Okay, fine. So I will have a try and share my screen.
Yes, let's try.
So, a moment, the talk has gone. There it is. Now you see
Good.
it?
Good. Yes. Okay. The next speaker is Jenny Wagner from Heidelberg. And okay, so he's going to talk about the morphology of these dark matter halos in galaxies.
Right. So hello, everybody, and welcome to part number 2 for today. I hope Andrea convinced you that our current cosmological standard model is still a sufficient means to explain all the puzzling observations that we have in our universe today. So we do not need to include further new physics in order to explain these phenomena. But taking a look at the current cosmological standard model as it still bears some mystery. And dark matter is definitely one of these mysteries. So because so far, dark matter has only been a mischievous grin in our universe. If we interpret and evaluate galaxy rotation curves, the cosmic microwave background, the weak gravitational lensing data, or strong gravitational lensing, dark matter only shows up as a missing mass in all of these phenomena. So everything we have is indirect observational evidence for this dark matter. But on the other hand, we have a lot of different complementary data from different epochs in the universe in order to consistently hint that there must be something which we call dark matter today. But how can we probe something that we cannot directly observe? Because so far, a significant direct detection is missing. We can use what I call the cosmic trinity to infer dark matter properties. So we start with our indirect observations, which provide us evidence to guide and test the hypotheses that we have about dark matter properties. And Andrea showed you in his talk that numerical simulations are the best probe that we can have at the moment to probe these dark matter properties. Because numerical simulations provide us with mock observations, which are based on certain evolution processes, which again are based on fundamental physical principles. So with numerical simulations, we can reproduce the evidence that we have in the observations. And if we have a good match between the mock observations and the real observations, then we know how and by which evolution processes these indirect observations can come about. And now I would like in my talk focus on the second baseline of the triangle. I would like to focus on the mathematical theory, which provides explanations which of these fundamental processes and principles that we put into the evolution process in simulations is necessary to produce these observations and which ones are sufficient to produce the observations. And hopefully for very simple cases of our indirect observations, I hope that mathematical theory can also provide a direct explanation, for instance, in a closed form theory. So that's how we can infer dark matter properties. Now let's focus on a very specific question, namely, what shape does such a self-similar dark matter halo have? And when we go to our indirect observations, which we have, for instance, from strong gravitational lensing or from galaxy rotation curves, we find a whole bunch of parametric fitting functions which describe relaxed dark matter halo mass density profiles. You can see some of the names of these profiles here in the red circle. If we go to numerical simulations and ask what kind of description do you find there for relaxed dark matter halos, we find another bunch of parametric fitting functions that you can see here in the yellow circle. If we go to mathematical theory, we actually have some fundamental theories and dynamical theories to explain some profiles by fundamental principles. You can see them in the blue circle. So today's goal now is to answer the question, is there one model based on fundamental physical principles to describe individual dark matter halo mass density profiles? And if this can be achieved, can this model explain why all of these fitting functions actually are good fitting functions? Because when you take a look at all the equations that you have for them, they are very similar. So let's first start with our goal to define what is a dark matter halo. What do we call such a structure? And I say it's a description of a static spatial configuration of a bunch of particles, just like in simulations. When you have your simulated bunch of particles at one instant in cosmic time, like you can see here, then you can ask, how do these particles cluster? So you set up, for instance, like here in the green circle, in the blue circle, and in the red circle, 3 dark matter halos at a certain moment in cosmic time. At another certain moment in cosmic time, you can find another clustering configuration and so on. That's what I call a dark matter halo in the following. And the same is actually done in simulations. And if you take a look at these snapshots, you find that these dark matter halo mass profiles seem to follow an almost universal density profile. And this is usually characterized in simulations, as you can see here, by the slope of this mass density function, which is defined as you can see here on the y-axis. And this is usually plotted over the radius with respect to the central point in such a dark matter halo. So if we now are supposed to set up a mathematical theory for this, we have to reproduce certain values of the slope parameter gamma. Starting from the outskirts, so from the outermost radii that we have in such a dark matter halo, we have gamma values of about 3 to 4. This we have to reproduce in our theory. When we go inwards, we also find that the simulations agree that in the intermediate regions of such a halo, we have an isothermal slope of gamma equals to 2. And now, when we go to the central part, even for dark matter only simulations, we find that the mass density profiles that we have, these fitting functions, they do not agree on a unique slope in the central part. There are, for instance, very cuspy gamma values for some profiles between 1 and 2. And there are some shallower profiles for other models, which are like 1 or even shallower. So our new fundamental theory that we set up should make a prediction. Is there one unique gamma value in the central part of a dark matter halo? And if so, what is it? Because the heuristic fitting functions here, they do not agree. And we know that here in the intermediate regions and in the outskirts, we should reproduce the gamma values that we find there. So that's the evidence that we have. Let's see whether we can find a mathematical model that matches these prerequisites. Of course, we start again in a similar way as simulations do to set up the mathematical theory. We start by having a microscopic ensemble of particles with a very simple approach to have a finite number of NP identical and identically distributed point particles. And as Andrea already mentioned, these are usually collisionless. And in the language of mathematics, collisionless means independent particles. And now comes the most important ingredient, which sets the entire stage, namely, we assume that Newtonian gravity is the only interaction between these particles. And this is very important because on the one hand, we do not know whether these dark matter particles undergo other interactions, like for instance, the weak interaction. So let's stick to gravity as the only one. And we know that our structures are usually much smaller compared to the Hubble radius, so that we can say Newtonian gravity will be a good description in this approximation of our structures that we are interested in. And this Newtonian gravity is now responsible for the fact that when we have all the pairwise interactions between our particles in this ensemble, we can make a linear superposition of all of them in order to arrive at the entire gravitational interaction in this dark matter halo. So that's the microscopic part, our particles. And now we have to set up a macroscopic dark matter halo model, which kind of is a compressed version, compressed description of all our microscopic ensemble particles. So we now coarse grain and compress the information in this microscopic picture to the macroscopic dark matter halo model. And for the sake of simplicity, I assume that my halo is a sphere. You can take any shape you want, but just the equations will get a little bit more complicated. So let's now assume it's a sphere and it has a finite radius r max. And then we know that we have Newtonian gravity here as our interaction, and Newtonian gravity is a scale-free force. And we know that scale-free forces cause self-similar structures. And this now means that self-similar structures are usually described by power laws. So this motivates now that we can describe our probability of one particle to be at some position Rj in this dark matter halo to be proportional to a power law profile. So we set up our probability density function for an individual particle to be at one radius in this dark matter halo to be proportional to Rj divided by some scaling radius to make Rj dimensionless. And here we have our power law index, which I now call gamma. And now we have a normalization factor here in this probability function, which encodes our halo geometry and the region where all these particles are supposed to be. Because the normalization here is taken to assume that if I take a look at a particle which is at a certain position in the halo, and then the probability should be 1 that I find it in this halo. And so the normalization factor gives me the macroscopic halo model here in this PDF. Now, this was just one particle. Now let's go on and assemble the whole bunch of particles. So we take a look, how can we set up the joint PDF for all the particles? Well, we have a lot of independent particles, so we can just multiply all the individual PDFs that we have here. Then we can take the logarithm to obtain the log likelihood of the joint probability density function of the entire particle ensemble. And now we can ask, what are the most likely and the least likely gamma values for our particle ensemble? So you get a maximum likelihood estimator as standard in probability theory. And if you insert the PDF that I just showed you on the last slide, you finally end up with this maximum likelihood equation where gamma enters here in the first term and the second term is phi of gamma. It looks a bit ugly, but it has a very deep physical interpretation, because in the first term here, there you have your macroscopic halo model, you have all the geometry and the region where the particles should be. And in addition, this normalization factor also depends on your gamma law, on your power law index, which enters this equation in this term. And this macroscopic part of this equation is then connected to the microscopic ensemble of particles, because here you have all the individual particle positions and the number of particles that goes in here. So you can solve for your most or least likely gamma in this equation now, dependent on the particle distribution and dependent on your halo geometry. So now we just need to know, how is this probability theory connected to our actual dark matter mass density profiles? And this is just one line, because assume that you have your particles and these particles sample your mass density distribution of your halo at certain points. So the density of a dark matter halo in this picture is given by the mass of one particle times the number density of particles at the certain radius. The number density of particles is the number of particles times the probability density function that one particle is at this radius. So now we have a direct proportionality from our density of the dark matter halo to our individual point particle PDF that I just showed you. So our power law index that we solve here in this equation is exactly the slope of our mass density profile that we have here in our theory that we would like to calculate. So with this line, we can now see what comes out for gamma here when we solve these equations for different particle configurations. Let's have a look. If we insert our halo geometry, assuming that it's a sphere of finite radius or max, then we get out of this equation here that gamma equals to 2 plus a ratio in which enters the finite number of particles and the distribution of particles with respect to this maximum radius of our sphere that we assume to be the halo. Now let's take a look at the different regimes that we have in each halo. We start with the innermost central part, which is usually very small, and it has a certainly finite number of particles in there. And if we take a look at this equation, if this is finite, then gamma is completely determined by the distribution of particles that we see here with respect to our max, which is now the end of our core. So this is here the central part, which ends at our core, let's say. And so this now becomes clear why the heuristic mass density profiles that we had in the beginning, why they cannot agree on a certain gamma. Because depending on which halo you have different distributions here, and then you get different sorts of gamma. And if you take this gamma equals to 1, this special case of a Navarro-Frank-White profile, this can be obtained if we have a uniform distribution of particles in the radius. So this is the central part. Now let's go on. And if we now go outwards in radius, we will encounter a lot more particles, because there the sampling gets better and better and we put in a lot of particles. So let's now assume that the number of particles in this region goes to infinity. And then we get that gamma equals to 2. And there, you remember, we encounter our isothermal slope. So this region where we should reproduce our gamma from the beginning is certainly fulfilled. Now let's come to the outskirts. In the outskirts, we have two different cases. On the first hand, we can assume that we are on very large scales, so for galaxy clusters, and assume now that the gravitational interaction actually goes to infinity. So our maximum radius of all particles that we should account should be at infinity. So each particle, no matter how far it is, feels that there is some dark matter halo here acting on this particle. So let's take a look what happens if we let our max go to infinity. Then we encounter that gamma equals to 3, which is actually the outskirts behavior of the Navarro-Frank-White profile. And so we have reproduced our typical behavior for galaxy clusters. Now let's take the other way around. What happens if we have a radius, R max, which is much too small so that the particle distribution actually spills over this radius? You can take an analogy. When you want to classify the brightness profiles of galaxies, you usually take a half light radius to characterize these galaxies. Now assume you have here a kind of half mass radius. Then the particle distribution will spill over. And if we have this like half mass radius, we encounter that gamma then equals to 4, which is exactly the behavior of the outskirts of galaxy scale dark matter halos. So in the end, we can see that this very simple probabilistic model is able to explain why the mass density profiles that we have, these heuristic fitting functions, why they do not agree in the center, that why they have an isothermal slope in the intermediate regions, and why the outskirts behavior is a little bit different depending on whether we are looking at galaxy scale dark matter halos or whether we are looking at galaxy cluster scale dark matter halos. So this is rather a point that how we choose our max, how we choose our radius to be, then we get these different behaviors. So in the end, we can summarize that it is possible to describe dark matter halo profiles from fundamental theory, and the approach so far separates the structure and its dynamics, as you have seen, because we just take snapshots at cosmic time, and then we describe the structure as it is there. So the shape description as it currently is independent of the cosmic assembly history. But as a kind of like disadvantage is an effective mean field approach. As Andrea already said, we have a lot of scales to cover, and numerical simulations can do this in a nonlinear way. And this here is just an effective mean field approach to describe the final state. But we have a clear understanding of dark matter halo shapes by means of a little set of parameters. And intriguing point here is I just introduced everything in terms of mathematics, in terms of probabilistic theory. But there is a connection to statistical mechanics, and you can express exactly the same stuff that I showed you in terms in the language of statistical mechanics. And then everything is exactly the same, and you get the same conclusions, but for physical picture, it's a little bit more intuitive. So stay tuned for paper number 2. This will be about the connection here. And what I think the advantages so far that this approach has is that it's very close to simulations. because we are including all the affinities that we have. We have a finite amount of particles, we have a finite halo extension, and we can control all these finite parameters and at some limit, let them go to infinity, but we do not start at some very rough coarse interpretation of this is already infinite or this is already zero. We have everything finite and non-zero and non-infinite. And the most intriguing point here is that this description avoids conservation laws and it avoids undefinable quantities, because I have not talked about any phase-space trajectories intertwining the information of positions and of velocities. Because to determine a density, it's sufficient to use the positions of the particles, or on the other hand, it's also sufficient to take the velocity information, the kinematical information. But you do not need both at the same time, because one set is already enough. And if you want to determine the density from the velocity distribution, what you usually do is you take a conservation law, for instance, like energy conservation, and you translate the position information by means of energy conservation to the velocity information. And then you're also able to determine the density. And so this approach here avoids this conservation law, because I first stick just to the positional information. And the best thing, we do not need to talk about entropy, and we do not need to talk about equilibrium, because usually 3D gravity has no thermal equilibrium. So how can we define this? This is usually a problem in standard approaches. And this approach doesn't need to define it. Neither does it to have an entropy, as you see, because we are just working directly on the quantities that we have. And if you are interested in getting to know a little bit more about the rough details, about the connection to statistical mechanics and so on, have a look at my essay, which was honorably mentioned at the Gravity Research Foundation. It's in there. And if you want to see the equations, then have a look at the full paper, which is published in General Relativity and Gravitation. Now, I'm very much looking forward to an interesting discussion. Thanks a lot.
Thanks. Very nice talk. Do you have a question for Jenny and also for Andrea in general? Please just speak.
So thank you for that talk. I have to say I'm confused.
Yes.
Because, you know, if I read about analytically modeling galaxy halos in a textbook, I immediately embark in phase space.
Yes. Yes,
So
you do.
Why does everyone else go the phase space route if it works without doing that? Which is what you seem to be telling me.
Yeah, I thought about this actually quite a long time. And I think the reason is the following, because our whole thermodynamics, which these kinetical approaches are usually based on, they usually use this phase-space approach, and they define an entropy. And this entropy is a potential from which you can derive all other quantities. And this works for all forces except for gravity. And so people thought, okay, if this phase-space approach doesn't work for gravity, we just have to make it work. And so people try to have like pseudo entropies or whatever, and always try to use this phase space, because thermodynamics lives on counting possibilities and occupation numbers in this phase space. But actually, I think it's kind of like a double information, because in there you have the positions and you have the velocities. And from the mathematical point of view, if you know the positions and you know a conservation law, then you also know the velocities and vice versa. So they are kind of like two sides of one medal. And so I think when you use a phase-based approach, you just want to have both, but you always correlate them. As Andrea already said in the simulations, you have to account for all the correlations between the x and the p-values. And this makes simulations also quite difficult, and further mathematical approaches also. And I hope that this is the right way to go, to separate the structure description and the dynamics. And that's why I think this approach has a good chance to work, because we are making it less complicated.
You have other questions?
Oh, and by the way, condensed matter physicists do this. So I stole it from the condensed matter people because they told me, like, why are you always intertwining all this information? We separate it. We have, on the one hand, we have the structures, and on the other hand, we have the dynamics. Try it like this. And that's how I was motivated to set up this approach.
Sorry, I'm confused about yeah, the last part. Maybe I just didn't understand. But are you saying that the equations are effectively first order and not second order?
What do you mean by first order and second order?
The you know, the equation of motion for the trajectories.
And there is no equation of motion so far in this approach.
Well, but you know, it's a statistical mechanics of particles, right? So they must obey Newton's equations.
Yes.
Yes, and you're saying that we shouldn't go to phase space since the velocities are determined by the position.
Yes, because if you have the positions over time, then this is nothing else than a velocity, right?
Yeah, I guess then I didn't understand where.
The idea is we want to describe a density, so rho of x. And what do we need? What are the necessary ingredients to define a density? And this is just to know the mass at each point in a volume. And so at first hand, we do not need any velocities in there. And that's the start of this approach, to say, okay, we leave the velocities completely aside because we are just interested in a structure description. So we are counting particles, their mass at certain positions.
But these that, okay, but so you are basically defining the Lagrangian velocity of a fluid element, which is the first moment of the distribution function, the usual distribution function.
Could do it, yes.
Okay. I'm just trying to understand the idea.
Yeah, it's actually it's a bit different from the standard, because fluid element, this means that you already suppose that dark matter is a fluid, but here we still have the particles, and the particles are just at a certain position in space, and
Yes.
then the dark matter halo, this density that you see here, that's actually then the kind of like fluid where we say that the particles just sample this continuous distribution at certain points.
Yeah. Okay, I understand. So, I mean, I guess this is what I would call the zeroth moment of the
Yes.
phase space distribution. Okay. I see.
Yes.
Okay.
Do you have other questions?
Yeah, I had a question.
Yes.
Yes, please.
Hi, I think it was a really good talk. Thanks a lot. I had sort of two questions. One was related to one of the things that you mentioned earlier, that you don't need to go through the entry. You could write down an entropy just in terms of the probabilities. So that's you could sort of recast the whole thing in an entropy language if you connect probability to, I mean, like rho log.
The problem with an entropy.
That's one question. Yeah.
So let's just start one by another. The problem with an entropy is that you need to define some kind of interaction length, right? You need to have a scale for the entropy in order to set this up, and you need to have an equation of state for this, and this doesn't work because 3D gravitation. There is no entropy in the common sense as we usually define it in thermodynamics, and that's the problem why I try to avoid it.
Okay.
I mean, in principle.
Yeah, and my second question. Yeah, so go ahead. No. Please go ahead. Yeah.
Okay, I was just saying that it's a question like when you have masses and these so when you have the Poisson equation, and then you have the potential and you have the masses, and so the potential is given by the density, and you can ask now, what is the potential given a certain density? And I think the entropy is an analog of this potential. And what's happening actually doesn't happen on the basis of the potential. The potential is just a good description for it. But usually we care about masses and where they move. And so I think this is why it works, that we can avoid to define the entropy. We are just concerned about what happens directly in the things we can observe.
Right. So in position space, okay.
Yes.
Yeah, and also I was a little confused because there's no lambda in this framework. So I mean, does that? So how does, I mean, does the picture depend at all on there being a lambda in the background? Because I mean, in principle, this whole thing is just for purely Newtonian.
Yes.
Cold dark matter, self-similar. So if you introduce lambda, possibly there is a violation of.
Yes.
Some of
Actually, Andrea and I, we had started to discuss a little bit because we think Newtonian gravity is a scale-free interaction. And in general relativity, there is a scale introduced. And so maybe general relativity also breaks the self-similarity of these dark matter halos. And this is something that we should investigate further, whether we would expect different kinds of halo shapes if we had general relativistic halos. But so far, everything is based on Newtonian gravity, and this is the fact why we get the self-similarity in the dark matter halos.
Right. That's sort of the basis behind the Botchinger self-similar solutions.
Yes. Yes.
More Goldwig and those ones. Yeah.
Yes.
Okay, great. Thank you.
You're welcome.
Yeah, both the talks are very good. Thanks.
Thanks. There are other questions? Okay. I don't see any other question. So thank you very much again, Jenny and Andrea. Very nice talks. And
thanks a lot for having us.
Thank you for your attention. Yes, and enjoy the rest of the day.